do it. And there are multiple metals, but we need also purity on the metals and all. So that was the idea that we had. Now, once you separate all these electronic components from the board, you can see that I have classified like different electronic components. If you take resistors, typically based on different types of resistors might contain bismuth, lead, nickel, ruthenium and all. So one good thing is, rather than processing everything together, if you can separate all the resistors and if you process it, then you can easily recover nickel or ruthenium nicely. And similarly for capacitors, basically most of the capacitors contains aluminum and tantalum. Basically tantalum is one of the important critical metal. So if you can separate capacitors, then you will have significant amount of tantalum. Now if you see the composition of tantalum in PCB, it would be in ppm level. But if you take only capacitors, then it would be like several thousand ppm. So recovering would be very easy. And similarly transistors are there, inductors, switches and all. Remember one thing, if you see these kinds of switches, this has gold. We always think that only microchips and RAMs have gold, but even this switch has small amount of gold also, only these kinds of switches. And there are diodes, light emitting diodes, transformers and all. And there are other things else, like batteries. In batteries you have lithium and all, you have rectifier, fuse, relays and all. So you have lots of metals. Now our ideology was like, we can't focus on all the metals and recover. At least if we can focus and remove significant quantity metals in your downstream step, other electronic components, you can separate it out and you can recover it. So this was the ideology we had. So I did a lots of literature review and I came up with one simple process. So if you see this covers all the entire literature review on PCB recycling. So I have designed it such a way that if you come through some process, for example, if you start from PCB and if you typically come to here, this will be one research article. Like that, I have processed it all mechanical separation process in one side and metallurgical process in one side. Probably in your mineral processing course, you will learn about all these mechanical things. And in next lecture, Ashok sir will be covering more on pyrometallurgy. I'll be focusing more on hydrometallurgy. But I'll just give brief overview about how do we do this mechanical processing and all. So I'm just going to zoom in the top part and I'm going to discuss. So we take printed circuit boards. And typically when you take old TV or old radio PCBs, it has lots of dust. And if you directly take it for hydrometallurgical process, this dust mix with acid. So typically you sieve it and you take these fines for further processing. Once you have these fines, it's like a fine powder. Most of the small dismantlers, what they do is like they come till this fine powder, they separate metallic fraction, non-metallic fraction, and that they call as black mass, and they export it to Japan. Especially in Tamil Nadu, there are like several startups who are doing this and they are exporting, they are selling it to Japan for recovery of copper and precious metals. So now the separation process. One is flotation, this is based on density that you might have learned in mineral processing. Second one is gravity separation. Basically you will use cyclone separator or air classifier or anything. Third one is electrostatic separator. In electrostatic separator, the typical idea is to separate conducting and non-conducting materials. So if you use eddy current, basically it gives some magnetic field that says that you should not use ferrous metals. So if you are using eddy current separation, then there should that is available. Hydropyro. So do you know the difference between hydropyro? Yes. Yeah. So hydrometallurgy means they added chloride, they added cyanide. So different chemicals they add to recover individual metals. So if I focus and if I tell, you can see that in all the steps, additional chemicals are added. The more chemicals you add in hydrometallurgical process, the difficulty in effluent treatment. Eventually, once you recover these metals, the solutions that you are getting creates a problem. That's one challenging. So when these types of it is called as zero discharge process. Our ideology was to develop a zero discharge hydrometallurgical process. Then I summarize some more literature. Precious metals. The reason why is it is expensive, but no one is focusing on critical metals. That's one thing I wanted to show. And you can see that the red color one that I highlighted is about the additional chemicals that they are using in the process, and typically these are sometimes very difficult to deal. If you go with sulfuric acid, then the material of construction of reactors should be one material. The tubing, the pumps, everything should be acid resistant. So when you scale it up, you have to address all these challenges and all. I will tell those challenges with nitric acid also. So there are several chemicals. The more chemicals, no one discusses about effluent. Their focus is only on purity of this one. They say that I recovered gold from printed circuit boards, I did amazing research. So these were the ideas we had when I did literature review. So everyone focuses only on precious metals, but certainly it also has some critical metals. Other than this, it also has some base metals like iron, aluminum, and also toxic metals like lead and all. So we have all these things. My ideology was only one thing, to develop a sustainable process. Sustainable means it should not harm the environment, and scalable process. It has to be scaled. Once this is there, you typically know pyrometallurgy process. It is energy intensive and releases flue gases. So people who do hydrometallurgy, they always say that pyrometallurgy is energy intensive, we should not go. But in fact, if you see industrial maturity is there because it doesn't have any cover. Whereas copper has a epoxy layer cover. You understand, right? So other metals have some resistance over it, some plastic coating or some epoxy layer, but lead and tin has direct contact with acid. So we wanted to use this as an advantage and we wanted to develop a process. So we took printed circuit boards, no crushing, nothing. Just dissolve in 2 to 2.5 molar. Because less than 2.5 molar, it has poor oxidizing properties. And we dissolved, so I call this first step as primary dissolution. Once you do this, you can see that tin reacts with nitric acid and forms hydrated form of tin oxide, that is H2O.SnO2. That is a precipitate. And lead reacts with nitric acid and forms lead nitrate. And you can see that there are NO2 gas that is released. And I didn't write reaction with copper because rate of reaction of copper when acid concentration is less than 2.5 molar with a resistance of epoxy layer is very slow. No copper gets reacted at this condition. Only tin and lead gets reacted. Now I got this colloidal solution where tin oxide is there, lead nitrate is there, and unreacted nitric acid is there. Now I have to separate one at a time. So when I leave it for some time, like it took almost 24 hours. You can see that all the colloidal particles got settled down and there's a top solution. When I take this top solution and do some ICP-OES or AAS analysis, you can see that it has significant quantity of only lead and very minute traces like less than 10 ppm of copper, iron and tin. That says that solution contains only lead nitrate and nitric acid. Then we separated this and when we dried it, we got the stanic acid. When we did EDAX analysis and all, it clearly confirmed that it contains only tin and oxygen. So this stanic acid has a very good market value. 1 kg is around 3,500 to 3,600 rupees. So I can sell this as one of my product. So I have already recovered one of my product from printed circuit boards, and it doesn't have any metals. So now after doing this, so I separated stanic acid, one product, green color one, and I have a solution of lead nitrate and nitric acid. Meanwhile, parallelly there is NO2 gas. This NO2 gas, I wanted to do absorption. Basically, if you dissolve NO2 in water, it forms nitric acid. But when you see the stream, that blue color line that is coming, right? The concentration of nitric acid is very low there. It's like 0.01 or 0.005 molar. What I will do, I'll take that and I'll mix it fresh acid and I can reuse it for primary dissolution. So that was the ideology. So now NOx gas is not released into environment. I will show you the reactor design also in some time. Now the next focus was on this stream where we get lead nitrate and nitric acid. So when we have lead nitrate and nitric acid, before this, one more thing. So here I told it takes 24 hours to enhance the settling rate, because I don't want to do at slow rates. To enhance the settling rate, we have modified this. Rather than using normal batch settling, we developed something called lamella clarifier. It's already there in industrial scales also. So typically when we have these inclined slides in this, the solid particles will touch this and slide faster rather than gravity settling. Sliding is faster rather than gravity settling. So this, when you use this, within 6 hours, you can see that all the colloidal particles got settled. So we were trying to see wherever is possible to enhance all the processes so that overall processing time will go down. So we developed this. Then later the focus was on the stream of lead nitrate and nitric acid. Again, we have to exploit something. I don't want to go with electrode deposition. The reason why is I have to add base. I don't want to use additional chemicals. How can we do this is we just exploited solubility of lead nitrate and nitric acid. So you have nitric acid in x-axis and lead nitrate in y-axis. You can see that with increase in nitric acid concentration, solubility of lead nitrate decreases. And I have shown it in two different temperatures. This is at 26 degrees centigrade and this is at 80 degrees centigrade. Now I have mixture, right? This lead nitrate, nitric acid. If I can separate water from it, then nitric acid concentration will increase. When nitric acid concentration increases, solubility of lead nitrate will decrease and typically it will crystallize. So that's what we did. We just did evaporation and we separated water. So initially when we did, we are at this point where acid percentage, like acid weight fraction is here and lead nitrate is here. Typically when you separate water, acid concentration will increase and lead nitrate concentration will increase. So we are supposed to come to this point, but lead nitrate is insoluble. Typically we fall here. So there won't be any lead nitrate in the solution, but it is precipitated out. That is this lead nitrate crystals. So we got these crystals, we analyzed it and it was like high pure, more than 99.5% purity. So we got one more product. So now I don't want to work with this. So the acid stream that is coming here, it is around 10 molar concentration now because I separated water, right? I can take this stream, I can mix with this stream and I can recycle it. So wherever I'm getting acid, I'm trying to take it, mix it and make up and I try to recycle this process. So till now I got two products, no liquid released. And I thought this process is very nice and all. Typically when techno-economic analysis, we found that this is an energy intensive process. Even evaporation means assume how pyrometallurgical process would be, how much energy intensive. And when you do calculations, we found that there is no profit, no loss situation. If there is no profit, no industry would be ready to buy this technology. Then we further thought that we should also recover copper. So this was the separation, that distillation, simple distillation unit that we used to get these lead nitrate crystals. We analyzed it. So now we had these printed circuit boards. After primary dissolution, it looks something like this. All the soldering got dissolved. When you vigorously shake it, all the electronic components get separated out. You can see that I have like lots of different types of electronic components on the boards. And if I focus on one board, this one, and if you take, you can see that copper below that epoxy layer. But I don't want to scratch and all, I just want to recover copper as it is. So after doing this, our idea was to separate these electronic components, and I'm not focusing currently on electronic components. If you want to recover precious metals or specific critical metals, you can segregate this and you can further process it. But first I'm focusing only on base metals. One is tin, second one is lead, third one is copper. So I take these kinds of boards and dissolve in 4 molar nitric acid. The reason why I went for 4 molar is, if acid concentration is low, rate of reaction is low. Above 2.5 molar, it has strong oxidizing properties. At that strong oxidizing properties, this epoxy layer, green color layer is there, right? It peels off. Below 2.5 molar, it doesn't peel off. If it is peeled off, copper is directly exposed to acid and copper will get dissolved. So that's the idea we had there. So it took almost 6 hours to dissolve all the copper present in that board. So we have a stream of nitric acid, copper nitrate, and you can see that this is the unreacted board. All the copper has been extracted to the solution and we have this board. Now I have a stream, liquid stream, which has nitric acid and copper nitrate solution. We did lots of things to optimize the conditions. So I did some kinetic studies to optimize the concentration, time, everything and all. So these are some pictures I will show. So these were the PCB boards that I have taken. After primary dissolution, you can see that all the electronic components were separated and we have this resin and all. Similarly, you can see that this is for different kinds of PCB boards. This is the final unreacted resin that we got. And you can also see that there are layers of this epoxy which is peeled off. So here it clearly shows it's not reacting with acid, it's just getting peeled off from the board. So typically it floats over the acid, you can separate it out. And all the copper got reacted. So this was one good advantage that we had, and we have patented this process. Then later, now I have a solution of copper nitrate and nitric acid. I want to separate copper nitrate, nitric acid, and I don't want to go for electrodeposition. Reason why? No more additional chemicals. So we thought, can we do liquid-liquid extraction? So basically, if you use tributyl phosphate, then what actually happens is like this tributyl phosphate is organic solvent. It tries to extract nitric acid solution from this. So I took this copper nitrate, added tributyl phosphate, mixed and I left it in separating funnel. Whatever nitric acid was there in this blue color solution has transferred to the organic phase. So you get a stream of TBP plus HNO3 and you get another stream of only copper nitrate. But the tributyl phosphate cost was very high. I think 1 liter was around 3,500 rupees. So now I thought, can I modify this? So what we did, we have modified this by adding kerosene. Kerosene is cheap, right? So 70% TBP plus 30% kerosene was giving same results as it is. So later we modified this and we were using. So now you have the stream of TBP plus HNO3 and you have copper nitrate. So you have copper nitrate, now you can do electrodeposition and you can recover copper as it is. Because you don't need to dilute also, because you have already separated nitric acid and all. Now this stream is there, right? I have to separate this TBP and nitric acid again. So how did we do is, we have added additional step called stripping. When you introduce water, this water will take all the nitric acid and you get a pure stream of TBP. This TBP can be reused again here, and this dilute nitric acid can be mixed with HNO3 makeup and can be reused. So this is clear, right? So basically I'm trying to separate nitric acid and trying to recycle it. And this TBP, though I am buying it, I am trying to recycle as much as possible. So I did experiments almost 8 to 9 cycles. I was using same TBP and its efficiency never went down below 87%. So that's the one good thing that we found. It's not 100% efficient, but it's more than 85% efficient, which was good enough for scale up. So once we had, so this is the setup I had in lab scale. So I have a reactor where NOx gas is there, right? So now I have to take out this NOx gas and send it to absorption column. So I create some negative pressure over the head of this such that it sucks all the NOx gases, and the inlet of this tube is right below here. So you get this NOx gas bubbles and it reacts with water and forms nitric acid. For safe side, if it is not completely getting absorbed, I have kept secondary absorption unit. Then I have connected it to vacuum pump, so that all the NOx gas gets converted. And for kinetic studies, I take samples at different times, measure the concentration and see whether it has reached saturation, complete copper got reacted and all. Now, one thing is, my primary dissolution experiment, I have to do only for 1 hour. If I go beyond 1 hour, other metals will start dissolving. In this, it was easy when I was doing in lab. After 1 hour, I take out and I separate, I filter it out and separate the solution. That was very easy. When we tried to scale it up, so here this was around 0.5 liters capacity. When we tried to scale it up to 2.5 liters capacity, we thought we should definitely stop the reaction at 1 hour. So we designed it such a way that we have kept a nozzle in the bottom and we wanted to collect solution. But what actually happens when nozzle is there, all these electronic components, colloidal solutions will choke the nozzle. If it gets choked, again all metals will start dissolving. To address this, what we did was, we took a perforated bowl, which means it's like a gas beaker with holes in it. We put PCBs in that and we place beaker as it is and we add acid, so that there is a filter between the solid medium and liquid. And when I open this valve after 1 hour, all the liquid solution gets collected in the bottom, and it is also connected to a big absorption column. So we got to know that size what I have to maintain, and we collected it. So we are collecting NOx gases and we are getting colloidal solution exactly after 1 hour. So this was done. Similarly, this is for lead nitrate evaporation. So we used some evaporation. So this was 0.5 liters capacity. Then we went for 20 liters capacity. This taught me so many lessons. The moment I got this, so I got this, and initially I did experiments with 8 liters of nitric acid. And when I was heating it, the concentration went to 8 molar and it was at 100 degrees. The first hazardous thing that faced is the valve in the bottom got broken, and it was concentrated nitric acid. Luckily, I was wearing safety shoes, acid resistant shoes and all. I know the challenges now. When I'm designing reactor, I have to make sure that that should not do. So I neutralized the solution. Somehow we cleared it. Then the vendor who fabricated it, he forgot to keep the secondary valve, safety valve. So I don't know about that equipment much. I directly reached out to vendor, he gave it. Then he installed secondary valve and we worked on it. With this ideology and challenges, we wanted to design a reactor. Now, once I have this technology, I have to see who are my potential customers, whom can I attract? Because I need some funding to do scale up research. Without that, it's very difficult for any academician, right? So we saw the typical products that we have is this one. And we try to find out what are all the applications of these products and who can be the users for these applications. When we were trying to do literature for this, I found that there is something called extended producer responsibility. I think all of you might know what it is. Yeah. So every industry has to recycle at least 20 to 30% of the waste that electronic waste. If they are selling like 100%, at least 20 to 30% of that they have to recycle it. So we thought, can we find some company who are actually generating electronics so that they have to recycle it, and this will be potential opportunity. And we showed that the products that we are developing has huge applications and all. Then we reached out to TVS Electronics, like that BPL. We have reached out to several industries. They come, see and go, but they were not ready to give funding and all. Eventually, Bharat Heavy Electrical Limited, Tirchi, they said, let's do one thing. We will just give some small seed grant of sort of thing. Can you slightly scale it up to 10 kgs level and show the process? If it works out, we are ready to help you, they said. The moment I got money, what I did was, I directly went to a local vendor in Chennai. I got the stainless steel 316 drum. This is of 100 liters capacity. I thought that I can do crazy experiments. I got big reactor and all, and this was just 15,000 rupees or something. And I had one experience of distillation column where there was a leak, right? I don't want that to happen. So I have put a tray here with stainless steel. If it leaks also, everything will be retained in the tray. So this was based on the learning. Now what happened is, like, this drum had like a huge size, and this was around 6 feet height, more than my height. Now I can't pour acid with hand like this. I have to do something. And this has like 36 nuts and bolts around it. When I tight it, all the 36 nuts and bolts, it takes me around 3 to 4 hours, because I just wanted to create vacuum such that it sucks all the nitric acid inside the reactor. And every time I was doing only fitting for 3 to 4 hours when I was doing these experiments. But this was something interesting. We got all expected results and all, only processing time, everything, it took lots of time. Based on this idea, we thought, anyway, we have funds now. Can we redesign the reactor design such that we can feed acid very easily, do it quickly, separate acid quickly, and separate solids quickly? So we came up with some new idea called tilting reactor, where I reduce the diameter. If I reduce the diameter, even though my PCB sizes are more, everything will be immersed. If diameter is high, my liquid level will be low. Complete PCB won't get immersed if I put it in standing position, right? So that's the reason why we thought that we will use this tilting reactor. So this has only 6 nuts and bolts. So I have reduced the diameter. Fixing 6 nuts and bolts, it took hardly 5 minutes. And we have planarized it with Teflon, all gasket and all, such that it creates vacuum very quickly. And we have used the stainless steel tubing, everything. So we feed acid from here, and after reaction, we collect all acid into the drum. So we have flexible stainless steel and all. So the reason why we went with stainless steel tubing and all was, here I was using Teflon. When I was using Teflon, after 3-4 cycles, even the Teflon was starting getting corroded and becomes rigid and it breaks. So we thought we should actually go with stainless steel. After experiment is done, again I can't put my hands and take PCB out, right? So we made it tilting such that when I turn it around, the reactor will tilt and all the PCBs will come out and you can collect in tray. This ideology was successful and we showed it to Department of Science and Technology. They said what you are doing is something unique and different. We are ready to fund, and we got 5 crores fund. Whereas they gave 3.3 crores in cash and BHL gave land and utilities, and they told start doing the project and scale it up. We hired several people to get the quotations and all, and we took third party help to scale up this and all. And we did some tilting reactor design, everything, and eventually we have set up a pilot plant. Now this is clear, right? We have a pilot plant where I have used individual like absorption column separately, settling of tin oxide, filtration, every unit we had to focus and we had to do. So every one person we have hired was working on one unit. One person was working on filtration setup, one person was working on absorption column, one person was working on reactor design, and all the scientific parameters they want I was giving: mass balance, energy balance, how much it costs, so where to control, what is the temperature, all the scientific parameters I am giving. And the third party vendors have helped us to set up this pilot plant, and this plant can process 100 kgs of PCB per batch, and per day we can process around 3 batches. It's around 300 kgs per day we can process. This was successful and we were able to recover lead, tin and copper. Now another challenge that we faced is we have like potential competitors, that is Hindalco and Tata Steel. I would not say potential competitors. What they have is like they have a very good team where business development team is there. They try to maintain this basically supply chain management. For us, we were not getting the raw material PCB, we had to buy. Whereas they went to Kabadi Walas, they told that we'll give you job opportunities if you give us PCBs collected. So they are doing and they are getting several tons. Now we have tied up with company called BPL. They said that we will give you PCBs, scrap PCBs, you can process it, and they were giving at optimum rate, and this is running in BHL Tirchi. And once this process started running and all, we again did techno-economic analysis based on the price that we are paying for printed circuit boards. If you are buying printed circuit boards, this process is not that profitable. So industry said that still it's a concern that we are buying PCBs. If it is for free, definitely we are going to make money. If it is not for free, then it's going to be a challenge. How can you address this challenge? Then they said that for one of their application, they were using copper nanoparticles and they were buying 1 kg of copper nanoparticles for 1 lakh rupees. 1 kg of copper is around 800 to 900 rupees, whereas 1 kg of copper nanoparticles is 1 lakh rupees. But certain terms and conditions. Those nanoparticles has to be of uniform size. If it is polydispersed ranging from 10 nanometers to 200 nanometers, then the price will definitely go down. Then they told we are already buying copper nanoparticles. Can you convert into copper nitrate into copper nanoparticles? That was another problem that I worked on PhD parallel to the scale-up research. So I'll just give brief overview about those copper nanoparticles and then I'll stop. So the challenge is whenever you go for metal nanoparticles, people work on gold and silver. The reason why is it's highly stable. Whereas when you go with copper, it gets oxidized very quickly. The moment you synthesize, within fraction or milliseconds, it gets oxidized and you get copper oxide. But we need pure copper because this copper is used in conductive inks. So if you want to make any flexible electronics and if you want to make conductive patterns, these nanoparticles are dispersed in these inks and they heat it such that it will melt and it will form like a thin conductive layer. So now our idea was to develop some process to convert copper nitrate to copper nanoparticles. And these copper nanoparticles are highly unstable. Now I have to do again literature survey from scratch and address these things. Then we thought, what are all the recipes that is necessary for copper nanoparticle synthesis? One is precursor. Precursor means the raw material. That is my copper nitrate solution. So I have Cu2 plus solution and I have to convert to Cu0. So we need some reducing agent to convert that. So here I don't have any other option other than doing this reducing agent. So I have to definitely use another chemical for this process. That's why we still didn't focus on scale up, but we are doing this. Then capping agent. Basically what capping agent does is it will try to form a thin layer around it and it won't allow that to grow. So it caps and all the nanoparticles will be Third one is solvent. Typically people use water. If you use water, copper gets oxidized quickly. So now I had to do lots of literature survey and see that what type of solution we have. This copper solution, then reducing agents. So we thought we will use ascorbic acid, which is a vitamin C, which is eco-friendly, and it's an oxygen scavenger. If there is any dissolved oxygen in the solution, it automatically takes out. And this is eco-friendly. So I'm using that chemical, it's eco-friendly. And next one is like I use some capping agents like PVP and all. And solvents, instead of using water, we were using diethylene glycol. The reason why I use diethylene glycol is solubility of oxygen in diethylene glycol is very low compared to water. So if oxygen is less soluble, then there is no chances that copper will get oxidized. So I had to find out all this recipe. Once I find out, then I have to optimize the conditions. So again, I had to do some research where I have optimized the conditions. So first I did batch experiments where I prepared solutions. I add certain sequence of chemicals one by one, and eventually we get copper nanoparticles. So now what happens is, like when I analyzed it, so basically we take it to transmission electron microscopy. The size of the nanoparticles were actually varying from 20 nanometers to 200 nanometers. When it is polydispersed, my market value will go down. Then what later we did was, we thought, can we go with continuous synthesis? So rather than adding batch wise, we were like continuously pumping into some different types of reactors, continuously monitoring, and we synthesize nanoparticles in this. So basically these are some of the flow reactors that I developed in IIT Madras. And then we have modified this to get much more precise size distributed nanoparticles, and eventually these are the nanoparticles that we got. So you can see that this is a scale of 20 nanometers. When you see the size, it's around approximately 6 nanometers, and this has a huge market value. Then industry said, can you scale it up? Now since I did it in microfluidics and millifluidics, scale up is like a bit challenging. That's the research problem that I'm parallelly doing in IIT Hyderabad. So this is the overview that I just wanted to give about PCB recycling technology. I think if you have any doubts, you can ask me. Yeah. Yes.
So as you said, you are directly just cutting down the PCBs into this process and you are getting.
Yes.
So I would like to know, did you run any studies where size reduction is also taken place and then
Yes.
is there any?
Yes, we did that. When we do size reduction, typically other metals get exposed to acid. If other metals get exposed to acid, I can't sequentially recover one metal at a time. Then I have to definitely add some secondary chemical to recover metal by electrodeposition. So our ideology was, don't use crushing, because electronic component should be as it is. If it gets crushed, other metals inside that gets exposed to acid. So that was the ideology we had. So we thought that we should not crush it and we have to directly use it, and no energy required for crushing. Yes, you had some question. This slide? Yeah.
So I'd like to share something from my side.
Yeah.
So you are using reducing agents or chemicals.
Yes, ascorbic acid. It's slower process, right?
It's slower, but yes.
So
We can get.
yeah, definitely we can get that. So the reason why I only went with this and not with that was, it's in exploratory stage. Second one is getting raw materials is also a challenge for scale up. This one is already available in market. So that's the only reason why. So we have explored actually different ways, but we went for this because we wanted to think in industrial scale up, because this is an industrial project and they were not ready to fund for publication. They were only ready to fund only for scale up. That's the reason why we did this.
Reading about the.
Yes. Yeah, the person sitting in front of you is my PhD student. So the currently we are doing research on that only, recovering metals using deep biotic solvents in IIT Hyderabad. So he's my first PhD student and he's working on the deep biotic solvents. Yeah. Any more questions? If not, I think we can take a break now. Yeah.
The retake down. So it is the direction for upcoming PhDs. So not
metallurgical engineering.